Hi there, and welcome to this presentation of Spacecrafts. If you've never been here before, this is a monthly talk series on some random bits of astronomy. We have a few sort of logistical details to go before we get started. As Sarah mentioned, there are t-shirts for you to buy. They're $18. Anything that you give us money-wise goes directly to outreach, all of it, because we don't take any for ourselves. Tip your bartenders, they will love you forever. Make sure there's lots of beer being consumed here because that just makes talks better. If a train goes by, they are usually loud initially, and so the speaker will say choo-choo and join the speaker in a chug of beer at that time. So without further ado, first speaker today is Patrick Kelly. Pat Kelly... Trivia. Oh yeah, there's trivia. If you answer want to answer one of the trivia questions that our speakers will have, raise your hand and shout out the answer.
Just raise a hand.
Well, raise your hands and we'll ask you to answer these things and then give you a prize. The prizes are cool, they're all astronomy themed, they're fun. So our first speaker tonight is Patrick Kelly. Pat did his undergrad at Harvard, then went to a little place called Stanford, which is now at Berkeley. So he's a smart guy. And he's been doing all sorts of cool things with stars that blow up, supernova. And he will be telling us all about a really, really cool supernova that he was the first person to discover. So Pat, take it away. Yeah, you can hold it here.
You should probably increase the
So I'll talk about this supernova that I discovered in the fall of 2014, which we named Supernova Refsdal, after a Norwegian astronomer who's predicted this kind of phenomenon back in 1964. And it's kind of fun to come back to Tucson because actually I was here at the astronomy camp on Mount Lemmon when I was in 8th grade. I was sort of when I first got interested in astronomy, so kind of nice to be back. But now I can drink beer. So I'll go through a little bit of the history of gravitational lensing, for people familiar with it. As far as we know, Isaac Newton really sort of first thought about this idea back when he was coming up with back in the beginning of the 18th century, and he wondered, well, do not bodies act upon light at distance and bend the rays of light, and is this not strongest when the ray passes nearest the body? And so he didn't really answer this question, and sort of within the Newtonian framework, it was addressed in the next couple hundred years. Cavendish, who was a famous physicist, sort of derived the Newtonian
There were no trains.
Okay. So he derived this formula right here, which predicts how much body will bend a ray of light passing by it. And you can see, that Einstein then came back when he was working on the general theory of relativity and revisited this question. And at first he came up with a number that was very similar to what the Newtonian picture would have predicted, and that was in 1911. But then he realized he had left out the curvature of space-time, which works in concert with time dilation to bend the light. And so if you have both of those effects together, you expect light to be bent twice as much as you would in the Newtonian picture. So this became a very exciting project to test, make the first test of general relativity. And that's what Sir Arthur Eddington did in these two 1919 expeditions during a solar eclipse. And basically they measured the position of the same star sort of before and after the eclipse, and saw that during the eclipse the star appeared to shift, and that shift, we thought, provided the first evidence for general relativity. So gravitational lensing, which is what this is a very important tool and has a very exciting history. And so that brings us to our first trivia question, and that is, what is the speed of light in centimeters per second? 30 times 10 to the 10 centimeters per second. All right. Well, okay, so back to gravitational lensing. So this was a pretty dramatic discovery or demonstration of general relativity in 1919. But people were, sort of had the attitude after that, well, that was great, but we're never going to observe this outside the solar system. And we're never going to see it for stars outside the solar system or galaxies. And, that's what the theorists thought anyway, even Einstein himself. But observers, don't give up and don't really care what the theorists have to say some of the time. And so this guy, Fritz Zwicky, who was a professor at Caltech in the 30s, sort of realized that galaxies and galaxy clusters, as opposed to stars, which is really what Einstein and other people were thinking about, would be much more powerful lenses. And so he sort of planted the seed of the idea, but at the time the telescopes were powerful enough to really look for gravitational lenses. And so it wasn't until the late 1970s when this first twin quasar image was discovered. And you can see the two bright sources in the middle, and those are the same background quasar, or quasi-stellar object, which is a black hole that's feeding on accreting gas. And so it's extremely bright. So we see it not once but twice, and that's because the matter in this lens here, this galaxy, is bending and creating two images. But it was really the Hubble Space Telescope that led to a revolution in gravitational lensing. A lot of these background sources, whose images are distorted and magnified substantially, are very faint, and so you need the Hubble Space Telescope to be able to see them because it's very good at picking out faint surface brightness objects behind lenses. And so you can see here this what's called an arc, a great arc, which was discovered in the 80s there with a ground-based telescope, was then re-imaged with the Hubble Space Telescope, and you can see it's much more dramatic, and you can see all kinds of other background galaxies. So it's been very exciting in the last 20 years to use Hubble Space Telescope. And so just to give some idea of what gravitational lensing is, if you have, say, a background source, there's the Earth, the light travels towards us on Earth, and then it's bent by this intervening source, and if that intervening source is collinear, well aligned, you'll see a symmetric, and it's a symmetric source, symmetric body, like a symmetric galaxy, then you'll see this nice ring, and that's called an Einstein ring. And so this is an example of a galaxy, which is lensing another galaxy, and you see this Einstein ring. But now imagine your source is not quite aligned, it's a little bit asymmetric. Well, then instead of getting this nice circle Einstein, you'll see multiple arcs of multiple images of the same background galaxy. So that's what you might see here, for example. And this is another example where you have multiple arcs of the same background galaxy. So this brings us to another question. This one's kind of tough.
A wine glass.
Yep. So it turns out if you look at if you take a wine glass and put it sort of the stem towards you, the diffraction of the light creates these arcs, and it's actually very similar to what you see in the sky with gravitational lenses. So it's kind of a neat way to, but of course these are really weird glasses. So here's another example of this very dramatic galaxy cluster in this case. So there are thousands of galaxies but it's the dark matter which actually accounts for most of the matter in these galaxy clusters that bends the light. And so you can see these dramatic arcs in the background of galaxies behind the cluster, which are being distorted and highly magnified by a factor of 100. So here's a nice video. So in this case, there's no lens, but instead here the photons are redirected towards Earth. And so we see multiple images. So you might see for a galaxy cluster, see these arcs.
Whoa.
All right, so I'm going to talk about supernovae, which is what I've sort of studied for the last 15 years. And we kind of borrow this.
Yeah, just unplug this.
You can move the table back, it's fine.
Okay, well,
Slightly closer to you.
I have this.
Yay! Science! Science!
Okay, so this guy, Supernova Refsdal, is the sole author of this paper, which is something that doesn't really happen these days. Usually you have 100 authors. He's a Norwegian astronomer, and he thought about what would happen if a supernova exploded in one of these galaxies that, where the lens creates multiple images of it. And he realized that if you measured the time delay between the arrival of the light from the supernova and the different images, that would be an extremely sensitive probe, both of the expansion rate of the universe and of the distribution of mass in the lens itself. So it's a way to probe the lens, and in some cases also measure how quickly the universe is expanding. So you can see. So no one had been able to find one of these for the next 50 years, and so. But I was involved in a search of galaxy clusters where it was possible we could find one. We didn't think it was very likely, so this is the November of 2014. Spotted one, and probably really hard to see. Anyway, I'll show you better. But so it's this galaxy that's lensed sort of near the center of the cluster, and then the center of the cluster is a really bright galaxy in the middle. And so there's an image. These are taken with the Hubble Space Telescope in the infrared. And the top image is one that was taken in 2011, and then we took data in 2014, which is in the middle. And then all you basically do is subtract the two from each other and see what has changed. And usually you're lucky if you find a single new source in your HST image. But in this case, we saw 4, so that was very exciting. No one had ever seen that before. And we wondered whether maybe it could be a problem with the telescope or some kind of an artifact, but we went back and looked carefully at the data. There's no evidence that there was a black hole that was accreting matter at the same position, which could have, created some variability. And so we were quite sure that this was the first multiple image supernova. And so here's a nice animation showing what happened. So the galaxy was 9 billion light years away. We think first there was an appearance of it in the cluster in 1995, and then we saw this next one in 2014 as 4 images, and that was because there was actually a galaxy along the line of sight which split the light again. But one of the more exciting parts of this is that we were able to make a prediction that we would see it again. So this wasn't the last appearance of the supernova, and that we'd see it probably again. Initially, we thought within the first 5 years, where people got all the modelers got together. There was a modeling derby of a sort, and everyone came up with their predictions, and they all sort of agreed it would be in the next couple of years. And so, we were able to write a Hubble Space Telescope proposal saying, well, we think it should appear here, given our best understanding of dark matter and everything else. Let's go look for it. So, I'll come back to that in a second, but first, something about the supernova itself, and this is a sort of a unique opportunity to study the early universe. This is 9 billion years ago, because the lens itself magnifies the supernova by maybe a factor of 10 to 20. Oh. So we're able to be way more sensitive than we would otherwise be able to be with just the Hubble Space Telescope, which is already very sensitive. But, so you can see in black, these are the light curves we often see of supernovae in the nearby universe. And so they have various different shapes, which depend on the star that gave rise to them when it exploded. And you can see that Supernova Refsdal just kept, instead of sort of plateauing or dropping, so a light curve is the amount of flux as a function of time. Instead, you can see the points keep angling upwards, and that means it kept brightening for months and months. And so this is a very peculiar kind of supernova, but it was actually reminiscent of one we've seen before. And actually, the most nearby supernova in the last 200 years that we've been able to detect. And that was supernova 1987A, which occurred in 1987 in the Large Magellanic Cloud, which is one of the satellite galaxies of the Milky Way. And this was something that was found in the southern hemisphere, but it was very exciting. And now I've been able to follow it the last 25 or more than that, almost 30 years. And study it very carefully. So we know a lot about it. We found the star which exploded. So it's kind of interesting that we can, probably know a lot about the progenitor of this explosion that happened 9 billion years ago, since it was quite similar to this one. So here's just a diagram of the lensing system, the light that traveled first to this more peripheral outside image, and probably in 1985, no one was looking then, so we don't know. But then we saw it again appear as this Einstein cross in late 2014, and then predicted it should reappear. And the modelers are very excited about this because this is very different from how, this is a very good test of their models of how we think the dark matter is distributed in the galaxy cluster and our understanding of general relativity itself, actually, because you need to use that prediction to, or you need to use that theory to predict how long it will take the light to travel through the cluster. And the reason that we thought this appearance in the center of the cluster would be last is because actually, even though the light takes the most direct route towards us, it's the last one to appear because of the curvature of space-time, so the photons have to travel farther, and also because of gravitational time dilation. So the time basically slows down for those photons going through the center of the cluster, where there's most mass. And so there are all these different predictions from different groups around the world about when the supernova would appear, see, they don't really agree with each other very well. So on the horizontal axis is this time delay in days, and then on the vertical axis is the relative magnification. So how bright will the reappearance be relative to the appearance in 2014? So we thought it would be fainter by about a factor of 4. So you can see here, this is an image from October of 2015. We started looking at the Hubble Space Telescope. Didn't see anything when we thought most of the models predicted something should appear. So we started getting a little worried. You can see the Einstein cross of those 4 red circles, and then we thought it should reappear in that other image, in the other red circle. And in fact, we waited a little bit longer, and it did show up. And so it was detected in December of 2015. If you go back in November, you can see some very faint flux there. So since then, it's been brightening quite a bit. And here's a more recent exposure, and you can really see that it's even gotten brighter than the old images, which have since faded away quite a bit. One other prediction was for exactly where the supernova would appear in the sky. And you can see here a bunch of predictions from different groups. And it showed up almost exactly where it was predicted by, especially this guy, Claudio Grillo, who's in Denmark. And so that was exciting that he really got it right. It's kind of fun. So this is the first time we've been able to predict the appearance of a supernova at a particular place and time in the sky. It's kind of fun. So here, going back to these predictions, from the early data, we were able to measure some constraint on this magnification and time delay, and you can see we were able to rule out a lot of the models. So inside these loops is where we think the supernova will eventually, or the time delay and magnification will be. And so we're continuing to measure the light curve and basically tighten these constraints. But it's a very slowly evolving light curve, so it'll take a while. And so back to the cluster. Here's the cluster. And so one of the things we're able to do then is compare these different models of the galaxy cluster. And most of the matter in the galaxy cluster is actually dark. So meaning we don't see it in light, and it's something actually we don't even understand what kind of particles it's probably made up of. But there are different ways of constructing these models using the galaxies as tracers of the dark matter, etc. And so here I'm just going to show you a couple of different ones that led to different predictions. So you can see some of the differences that are in the models. And by comparing these model predictions to what we actually see, we should hopefully be able to improve our models of these galaxy clusters, which in turn are actually among the most powerful cosmic telescopes, because of the ability to see the supernova, with very high signal to noise. We can also look for the earliest galaxies using these clusters as magnifying glasses. But we need to have a good model for the glasses themselves. That brings me to the final question here, which is also tough. And that's, what was the first good evidence for the existence of dark matter? Oh, yep, you got it. So yeah, so as the measurement of rotation curves of galaxies, the sort of how quickly they're rotating as a function of radius away from the center of the galaxy, pointing to the existence of this invisible dark matter, and that was really in the 1970s. Vera Rubin at Carnegie was the person who sort of pioneered that. And, so that's it. Okay.
So we've got plenty of time for questions if you have anything to ask Pat. What he did mention is he was looking at this data at like 2 in the morning when everybody else was sleeping, by the way. which is partly why he was the guy who found it first. Correct me if I'm wrong, but like he was just like, oh, this is like, you know, the best time to keep working when you have like a little young kid.
Oh yeah,
So,
that's true. Yeah, no, I have a 14-month-old. This is a little before that, but yeah, I was actually drinking a beer at the time.
Delay, differential delay through the center versus the outside?
Yeah, that's a good question. So I showed you the light curves before. So that's the flux as a function of time. So you measure that for each of these appearances, and then you basically just shift them in time until they match each other. And then you also magnify them. But
Do you need a transient band on the other side, or?
yeah, you need a supernova, or people have tried to do this with quasars as well. But usually so supernova is a nice clean light curve. It's bright. Quasars are feeding gas in sort of a stochastic, complicated way, and so you have to monitor it for a couple decades to really, in some cases, well, not in all cases, but yeah, you get these little variations.
I'm a total noob to this field, so I'll preface my question with that. How do you find this? In my head, again, I'm in a totally different field. I'm assuming you do some sort of digital signal processing and compare similar images of previous locations to look for changes. But I actually have no idea. So when you were at 2 in the morning with a beer and you found this, what is that? How do you find that?
Well, so it's actually not very high tech. At least Gotham might be using more high tech stuff for analysis. Anyway, so these are the two. So you have 2 images here. So you find one that was taken of this field a few years before, and then the one in the middle is the data we got from the telescope in 2014. That's actually, that may not be true, but something like that. So then you just subtract one from the other. So you have to register the images and then add them together and get rid of cosmic rays and all this stuff. But then you basically just subtract them from each other and then look for sources that are new, which you don't think are artifacts.
So follow-up question. One would assume every time you get a new image of someplace we've already looked at, you would run the same difference and apply all the algorithms to remove all the artifacts and what you know.
Yeah. And I mean, so the nice thing about this survey was the Hubble Space Telescope is very powerful, but it doesn't actually collect a very big volume of data. So in the next 20 years, this is what God's working on. The new telescopes are going to pull in huge amounts of data, and so you could never sort of manually look by eye. You have to use machine learning and everything to process the data quickly. But in this case, I just got to look at the image. I mean, I think the human eye is still maybe better than a machine.
Not for long. So, I mean, since Pat put me on the spot a little bit, this project that we're building, partly in Tucson, but down in Chile, called the Large Synoptic Survey Telescope. That thing has a camera that is as big, quite literally, as me. It is, the focal plane of this thing is my height. It has 3.2 gigapixels. So your cell phone has a megapixel or so? This is 3.2 gigapixels, which is an astonishingly bad number. Because it means that you get about the volume of 1 Google worth of data every year. And to try to sort out a Google worth of data by eye, I'm not going to do it. So this is why they made me the medium-sized box.
What was that before?
What, so I remember seeing a scale and it's up to 2 inches. I'm assuming that's like.
Arctic.
Okay. It was, okay then. So, but what was the size of the total survey?
Yeah, so this is actually an interesting survey where we looked at 10 different clusters. It's with something called the GRISM, and this is something led by a professor at UCLA. And so GRISM actually takes a spectrum, which gives you the flux as a function of wavelength. So you can look at the abundances of hydrogen, helium, etc., and tells you what the redshifts of objects are. So this took data of 10 different clusters like these, which are the best magnifying glasses, and was looking for these background galaxies that were formed only hundreds of millions of years after the Big Bang. So the supernova search was actually just kind of a sideshow that I was doing, so and we got lucky.
You got one more.
One more question.
So for the discovery of the late second appearance, was it an earlier time or a later time post explosion? And if it was an earlier time, can you use that to kind of fill in bits of the light curve that might have been missed the first time?
Yeah, that's a great question. So usually when you observe a supernova, let's say it's cloudy, and then you'll miss for a few days, and then you'll miss the first few days of the explosion. It'll be gone forever. In this case, we see the supernova appear again, and we know where it's going to appear, so we can actually see what happened in those first few days. And there weren't any clouds in space, but but yeah, no, I think. Well, so the reappearance is a bit fainter, so it's a little bit. I was working on this last week, but I think we caught it earlier because we didn't see it in October. We did see it in November, and so it will be helpful actually to try to understand more about the physics of the explosion and maybe even figure out how bright it was or luminous it was intrinsically. If we can figure out when the explosion occurred, and that we might be able to figure out from the reappearance. So I think we caught it earlier.
So if we don't have any other questions, I'm gonna have you all thank Pat again. So we're going to need a few minutes to set up for our next talk because not only does it involve a cool slideshow, we need to hand out red-blue glasses to all of you here because we have some cool stuff. So get another beer, get some pizza if there's any left, and
So
we'll
let's
be
start
back
back.
with you in 5 minutes or so.
Yeah. Okay, gotta be the- Okay, what do you want now?